Here is another example using Taylor polynomials. So here we want to construct a Taylor polynomial centered at a equals 0 for f of x equals sine of x of degree 5 to estimate sine of 0.2. Then you find an upper bound for the error when x is between negative 0.3 and positive 0.5. Okay, so the first thing that we want to be able to do is construct this Taylor polynomial. Now on Canvas, what I did, I uploaded some of the Maclaurin series for some of the most common trig functions, so and also some exponential and some logs. So you can go ahead and take a look at it, because remember that when a equals 0, this is actually just a Maclaurin series. So if you look at that, then you know that f of x is going to be, which equals sine of x, can be expressed as a sum from n goes from 0 to infinity, from negative 1 to the power of n, x to the 2n plus 1 over 2n plus 1 factorial. So I got this by, if you went ahead and just use the definition of Taylor series and you come up with some pattern, which is kind of what we did with the cosine a couple of videos ago. But this is the one for the sine. But I posted the Taylor series, or the Maclaurin series in this case, for the sine function. And basically what this is, what I can do is now I can expand it when n equals 0. Okay, n equals 0 is going to be x, then minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, plus x to the 7th over 7 factorial. Oh, that should be a minus. Okay, and then plus yada yada yada. Okay, so this can actually help you reduce a lot of different types of calculations, because if you already know what the closed form of this function is, then you can just go ahead and write down the series. Okay, if you don't, then you want to be able to do just a long way. And notice that this is only for the Maclaurin series. It's not for any value of a. It's just for a equals 0. So now here we wanted a degree 5. So we already have a degree 5 polynomial, which is just this guy. So we only want it up to the 5th power. So my t5 of x is going to be equal to x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial. Okay, so this looks kind of ugly. Okay, so that's going to be my degree 3 polynomial. So we just used it, and what we want to do is we want to estimate sine of 0.2. So sine of 0.2 is just basically, so I can't quite do this in my head. So what I'm going to do is I'm going to plug this into this polynomial. So t is going to be approximately equal to t sub 5 of 0.2. It's 0.2 minus 0.2 cubed over 3 factorial plus 0.2 to the 5th power over 5 factorial. Okay. So when I put this into my calculator, I'm going to get 0.19867, something around those lines. Okay. Okay, and now if you want to compare it to the actual true value, sine of 0.2, you can go ahead and do that. And that, well, I should probably put approximately 2, because, but if you just put the sine of 0.2, remember this should be in radians. This is what I'm going to get. Okay, so something to kind of just know is that the error is not that bad. So you can expect, you know, also 0.2 is really close to 0. So you can imagine that my values are going to be really nice. They're going to be not as far off. I'm also using a degree 5 polynomial, so I increase the degree, so it's going to be a lot better estimate. Okay, so so this is what I got. Now we're not done yet, because now what we want to do is we want to find an upper bound for the error when x is between negative 0.3 and positive 0.5. So let me just write that we want x to be from negative 0.3 to positive 0.5. We want to find an upper bound for this guy. And the way that we did it in the previous video, we said that we can use for the upper bound this remainder term. And this is going to be less than or equal to the absolute value of the n plus 1 derivative divided by n plus 1 factorial x minus a to the n plus 1. Okay, so we're going to use this guy to try to find an upper bound for my error. So now, since we used a 5th degree polynomial, n in this case is equal to 5. So we're going to have r sub 5 of x is less than or equal to. So when I plug in 5 in there, I'm going to get the 6th derivative divided by, I've plugged it in the bottom, it's going to be 6 factorial, x minus a in this case is equal to 0, to the power of, so 5 plus 1 gives me 6, okay? So now what I'm going to get is the absolute value of the 6th derivative of x divided by 6 factorial, x absolute value to the power of 6. All right, now all we have to do now is figure out what the 6th derivative is going to be. So you know that we started off with f of x is equal to sine of x, okay? Because that's what the original function was. It was just sine of x. And I'll leave it to you to try to figure out what this one is. These are not that bad, but I will tell you that the 6th derivative is just going to equal to negative sine of x. Okay, so that's what it's going to be. So this thing is going to be equal to, okay, the absolute value of negative sine of x divided by 6 factorial x, absolute value of x to the power of 6. Okay, notice that the negative is going to go away, so I'm left with the absolute value of sine. So I have the absolute value of sine of x divided by 6 factorial x to the power of 6. Okay, now the whole point of this whole upper bound is that we want to make this as big as possible. Okay, so you have to be very careful with sine, because the absolute value of sine of x, think about what is the biggest possible value that sine can give out. Now it's not going to be this upper thing. It's not going to be 0.5, because 0.5, well, you have to think about it. Is 0.5 the biggest number that sine of x can give you? No, the biggest number that sine can give you is 1. So if you look at the graph of sine, you can see that the greatest value that this will give you is at a 1, at x equals 1. So actually I can bound this sine by a 1, okay, instead of a 0.5. Divided by 6 factorial, what is the greatest value that this guy can give me, okay, that absolute value of x to the power of 6 can be. Now this guy, x, the highest value that x can be in this case is going to be 0.5. So what I'm going to do is I'm going to put 0.5 here, okay, so this is going to be 0.5 to the power of 6, okay. So all I have to do is just put this in my calculator, and I'm going to get 0.000021701. Okay, so that means that my error between these two numbers from negative 0.3 to 0.5, it cannot exceed this amount of error. Okay, now you might be wondering, what is the whole point of having this other term? Okay, so why do we have this term? Well, sometimes you may use this term. This term can actually be used. So for example, if this negative 0.3 will maximize this thing, then that's when I want to use that. Now you might be wondering, when is this going to maximize it? Well, if you had, for example, the derivative was like 1 over x to the 2/3, okay, which one will maximize it? Will it be the 0.5 or will it be the negative 0.3? Okay, well in that case it's going to be this negative 0.3, so we will plug in that negative 0.3 in here, because remember that the smaller the value on the denominator, the bigger the whole fraction is going to get. Okay, so that's just something to really keep in mind. So this isn't an easy thing to do. It does take a little bit of practice, but this is how you can find upper bounds.